Can you understand what I'm saying? So it is in this direction. And now when the current is going here, when it comes to this side, what happened? It is in the opposite direction. The current is here, it is going like that, and it is coming like this. But still I'm holding my pen because it is showing me what is the direction of the current, and therefore that can make out what is the direction of the magnetic field. So once I come here, can you see what is happening? It is in the opposite direction. Okay, so it is going to be in this direction. So when you look at it, obviously you know that these circles are becoming bigger and bigger. I don't want this to be, otherwise most of you are seeing here. Don't see that. See here. What do I do? Is that okay? Did you understand? So what is happening? You have here, I want you to concentrate this part of it. I want you to concentrate here. So you have these circles here. You have these circles here. And as we are moving away from the wires, we find out that the diameter is becoming bigger and bigger. Okay. So when you're actually looking at the center, you find that these are almost like straight lines. Can you see that? Those curves are becoming bigger and bigger, and therefore, right in the middle of the loop, you find that these are the ones, the magnetic field lines are almost becoming straight. Okay, becoming parallel. Therefore, you can make out that using this right hand thumb rule, you can find out what is the direction of the magnetic field current when you are using a coil also. Is that okay? Okay. Magnetic field line due to the current through a circular loop. Is everyone concentrating on that? If you are having, you don't want it, okay, better. Okay? Are you all ready? We have seen the pattern of the magnetic field lines produced. Did you all get it? Which paragraph did you all get it? Yeah, one by you want to read? Yes, read. Yes, read. Yeah, come on, read.
We have so far observed the pattern of the magnetic field lines produced around the current carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it.
Underline the statement. Inversely. What does it mean? If the distance is increasing, the strength is decreasing.
Similarly, at every point of a current carrying circular loop, the concentric circles represent the magnetic field around it would be it would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines.
Underline. What is happening here? What is happening to these arcs? Okay, because the size is increasing, somewhere in the middle here, you can find that they are almost appearing as if they are parallel lines. Yeah.
Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop.
Underline. Appearing as straight lines in the center of the loop.
By applying the right hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop.
Okay. So here you can easily make out that it is in the same direction. So in the center of the loop, obviously the magnetic field lines, they are in the same direction. Okay. Obviously because the current is moving up in one loop, but when you come across, it is moving down in the other loop. Therefore, the magnetic field lines will be clockwise, and here it will be anti-clockwise. Is that okay? Clockwise and anti-clockwise, if I use these two words, you should be quite comfortable. So if we are seeing about clockwise, so when we say it is clockwise direction, obviously we talk about clockwise. Correct? And if we say it is anti-clockwise, obviously it is going to be the other Because the direction, because in the left hand it is in the opposite direction. Magnetic field and current in this direction. So it doesn't move that. And with reference to the direction of the current. With reference to the direction of the current, it is always, how is it? It is going to be endless. Okay. Read.
So now, if I this is the that you called Maxwell's
One minute.
now that circular loop diagram, if we change the terminals, then
Obviously, it is going to be different.
also
See here, now, here, all of you refer to this diagram, okay? We have just started by putting this as a positive terminal. So we know that the current is moving up in this direction and we are going to be using our right hand thumb rule. We know the direction of the magnetic field is going to be in this direction. What happens if I change it? What if I change the terminal and I make this as positive and this as negative? So what will
right
happen?
hand rule will not be.
You have to still use your right hand thumb rule. Only thing is
Direction.
yes, you will notice that. Now see here, same thing, okay? Same diagram. I have just made this as positive and this as negative. So now what is happening? The current is moving up here. Correct? Did you all see? Did you all understand? It is moving up here. See? Did you get it? And the current is moving down there. So I'm still holding the pen. I'm still referring to my right hand thumb rule. Only thing is when I come down this line, it's going to be like this. So the direction of the magnetic field will change if I change the terminals of the cell. Okay, but still we are going to be using our right hand thumb rule. You are not going to change any of this. You are still going to hold on to your pen. You are still going to refer to this thumb and the curled fingers. The only thing that has changed is what? Only the direction of the current. In the first case, it was in this direction. Now what have I done? It is I've shifted the terminals of the cell. Therefore, in this loop, we have got the current which is moving down. Is that okay? Did you get it? Yes. Continue on.
This rule is also called Maxwell's Krotsky
Screw.
rule. If we consider ourselves driving a
What's
corkscrew
funny? Yes.
in the direction of the current, then the direction of the rotation of the corkscrew is the direction of the magnetic field.
Yes. Okay. Suppose you have got a nail which you have to fix. You want to fix a painting or something. Obviously, you have to drive a nail into the wall. Okay. Instead of using a nail, probably I have a screw. So what am I going to do? I'm going to do this. Correct? So it is the same thing. Did you notice what I'm going to do? It's going to be like this. And I'm going to rotate it like this. Did you understand? Okay. So this is definitely going to be showing you the direction of the current. And these curled fingers will definitely show you the direction of the magnetic field. The direction of the magnetic field. Yes, continue.
We know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turn, the field produced is n times as larger as the produced by a single turn. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds.
Okay. Let's say there is a question as to how we are going to increase the strength of the magnetic field here. Okay. Let's assume that the question is how are you going to increase the strength of the magnetic field? So there are two things. What are the two things? One is by increasing the number of cells. You increase the number of cells, what will happen? The cell current will increase. Okay. So first thing that you have to remember is by increasing the current I. And how will you do that? Instead of having only one, you may have a set of them, a battery of cells, which can increase the current. As you are increasing the current, obviously the strength of the magnetic field will also increase. What is the second method to increase it?
Increase the radius of
So what is the second one? You have just read, all of you have just read.
n times.
What does it mean? What does it mean? Read the paragraph again. Magnetic coil. Yes. Instead of having only one coil here, suppose I'm having many coils. Okay, I've got a bunch of wires. Suppose this is my cardboard sheet or whatever it is. Have a look at it. So I've said you're passing a wire, making a coil in that, passing it down. Okay? Instead of only one wire, suppose I make many coils. Okay? Obviously, each wire will have the current which is going through. If there are 10 turns, obviously the magnetic field is going to increase 10 times. N, did you notice the number N? Whatever times. Why? Because the current is flowing through each loop. Okay? If you're having 5, then obviously the current will increase. If you're increasing the current, okay, assuming that the current is remaining constant, but you have increased the number of coils. As the number of coils are increasing, obviously the magnetic field strength also will increase so many times, n number of times. Suppose you're having n coils, then obviously the strength of the magnetic field will also increase n times. Did you understand? Read the paragraph again. We know that the magnetic field, mark out your points. There are 2 points that I want you to understand. What is the question? What was my question? How we can increase the strength of magnetic field? Did you all get it?
but जो point पास करते हैं कि बार-बार तो तुम दो जो point बनाए उसी पास करना.
Yes. So what I'm going to do, I'm not going to take it and poke it every time. I'm going to take a long piece of wire. Okay, coil it many times, and then last में एक साथ I'm going to put it inside. ठीक है? Did you understand? Okay. Then we know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. So what are we talking about? And the current, okay, the quantity of current. Therefore, if there is a circular coil having n turns, underline that point. N turns is what? What is that n? We're talking the number. Okay, whether it is 5 or 10 or 20 or whatever it is. The field produces n times as large as those which is produced by a single turn. Did you understand? Whatever magnetic field is produced by one single turn, suppose you are having n number of turns, obviously your magnetic field will increase n number of times. Did you get it? Then, this is because the current in each circular turn has the same direction. Did you notice this? Suppose you are taking it, coiling it, making another coil, making another coil. Is the direction changing? No, it's not changing. Why? Because the direction of the current passing through each coil will be in the same direction, and therefore it is getting added up. Did you understand? Very important. Please underline that statement. Current will not add. Because the current is flowing through each coil is the same and it is in the same direction. The magnetic field lines, which is the strength of the magnetic field lines, will keep on adding up. Hello?
I'm explaining your video.
Yes. I told him. One minute. I have asked him to upload the video again. I've sent him the link also. He will do it. He will do it. Don't worry. Yeah, try to.
No.
Did you all understand that? Okay, circular coil. Put a Q in your textbook, and I want you to write it also in your notebook. I'll read you right now. Okay. Okay. And there could be a give reason why. Why is it adding up? Why is the strength increasing?
Because the magnetic field lines are adding up and the current flowing is much.
The strength about that.
Yes. So how do you express it? How do you say it? What is happening? As the number of coils are increasing,
The
the strength of the magnetic field is increasing. Why? Because the direction of the current is in the same direction. Each wire has got a magnetic field. Okay. So as you are increasing the number of coils, the magnetic field also increases at times. Did you understand? Very important. Please mark it in your textbook. Okay. Right. Now I'm going through activity 12.6. Did you all get that? Yeah. Good. Okay. Activity 12.6. Right? There's another activity. We yeah. Wait. Question.
Take a rectangular cardboard having two holes. Insert a circular coil having large number of turns through them, normal to the plane of the cardboard. Connect the ends of the coil in series with a battery, a plate, and a remote as shown in figure 12. Sprinkle iron filings uniformly on the cardboard. Slap the cardboard gently a few times. Note the pattern of the iron filing that emerges on the cardboard.
Okay. This is what they're talking. Correct? Here I've shown only one single coil, but instead of a single coil, they have taken many coils. Many coils passing through, and that is how we are talking about concentric circles, which is giving you the direction of the magnetic field. How will you increase the strength of the magnetic field? What are the 2 points? Sashi, can you tell me? Quick, you must be quick because we just now discussed how will you increase the strength of the magnetic field. How many of you know the answer? Put up your hand quickly. Hmm. Hmm. Come on. By increasing the number of coils. And second thing?
Increasing the current, adding more cells.
Yes, by increasing the current which is flowing through. Okay, did you get it? Take down the question in your textbook, notebook, whatever it is. Take it down in your notebook. Come on now, quickly, let me give you some written work. How many of you don't have the notebook today? Will you please take it down in your whatever book you have and stick up this paper or copy it down, right? Don't do that. Take a paper, stick it up. I'm not even asking you to do it up. Chalo. The first question. First question. How will we increase? How will we increase? Take down the question. Increase the strength of the magnetic field in a circular coil. In a straight coil, there are nothing you can eat. Okay? So we have to mention that it is a circular coil. Started. Tell me what is first point? How can you increase? Okay, by increase. First point, by increasing the number of coils. By increasing the number of coils. And your explanation you will write, if there are n coils, write it down. The field produced, if there are n coils, then the field produced is n times as large as that produced by a single turn. It is n times as large as that produced by a single turn. Okay, continue in the same point. Okay, this is because the current in each circular turn, instead of writing circular turn, you can also write coil. Okay, because the current in each circular turn has the same direction and hence the field due to each turn adds up. Add, ADD, adds up. It is adding up. Is that okay? Will one of you read what you have written? Will you read, Raj? What have you written?
If there are n coils, then the field produced is n times large
As large as. Come on, come on.
क्या हो गया तेरे को?
Abhishek, this is very bad. This should not happen.
I'm asking you what Ravi's dialogue is that? Ravi's dialogue, no?
Yeah.
Come on, come on, come on. Yeah. Chalo.
If there are n coils, then the field produced is n times large as that produced by a single turn. This is because the current in each circular turn has the same direction and hence the field due to each turn adds up.
Correct. That is the first point, right? Second point, what will be right? How are we increasing
Increasing the number of
Yeah.
cells in the circuit.
Also you can simply write by increasing the current. Right. Okay. By increasing the current is what is your answer. We are going to discuss now regarding the solenoid. Right? Now this component, what we are talking about is the solenoid, is going to be used in many of the electrical appliances. Right? Wherever we have a magnet, suppose we are using a bar magnet, right? Versus a solenoid. We see what are the advantages of a solenoid because the solenoid itself is behaving like a bar magnet. Is that okay? So in a bar magnet, you know that this is a permanent magnet. Whereas a solenoid is behaving like a bar magnet, but it is nothing but an electromagnet. Did you understand what is an electromagnet? Okay. So what is happening here? Look at me. This is once again your wire. And when you are passing current, it is developing a magnetic field. Is that it? So it becomes an electromagnet. Where there is a magnetic field due to electricity, it is called as an electromagnet. So your solenoid is nothing but an electromagnet. Okay? We have seen two important aspects. What are those aspects? Electromagnet is nothing but a magnetic field due to electricity. So we know that we can increase the strength of the magnetic field, isn't it? By passing more current or by increasing the number of coils, we can increase the strength of the magnetic field. Therefore, a solenoid has got a greater advantage as when compared to your ordinary bar magnet. Have you followed? By having a greater current or increasing the number of coils, we can also increase the strength of the magnetic field. Whereas for bar magnet, you cannot. Whatever the size of the bar magnet or whatever it is, it's going to remain. It's a permanent magnet. You cannot do anything about it. Here what happens? Which is a permanent magnet? Is this a permanent magnet? You think it is a permanent magnet? No. The moment you stop current, the magnetism is lost. So this is a temporary magnet, whereas the bar magnet obviously is going to be a permanent magnet. Is that understood? Here? Here? Obviously you cannot carry. Suppose you have to. Now listen to me. What about the applications? Okay. Such type of electromagnets are the ones which are used in your shipyards. I'm giving you practical applications so that you remember. You know what happens in a shipyard? You have to pick up huge containers from the ship and you have to transport. So you can use a crane, or in many times they are using an electromagnet. So they've got a huge electromagnet which can actually pick up the containers and put it there. Okay, or also in a junkyard, suppose you want to separate out, right, a magnetic, this is a magnet, and suppose you want to pick out all the ferro iron substances, it can easily do that. Okay, and we can change the strength of the magnetic field by increasing or decreasing the current. So a temporary magnet like a solenoid is definitely going to be useful as when compared to your permanent magnet. Why? Because you can
This
change.
has more strength than permanent magnet.
Sorry, obviously in industries you're going to use more of a solenoid.
Means the magnet, normal magnet, it has less strength than electric.
No. You can have even this bar magnets. I'm using only a small bar magnet, but actually, if you look at there are huge magnets. How big can you have a magnet? It's possible for you to have a very huge magnet, a permanent magnet. So that's where we are going to be talking about electromagnets.
मैम आप जो प्लेन की बात कर रहे हो तो the electromagnet जगह normal magnet यूज हो जाएगा.
No, we don't use it. We don't have such huge magnets at all. We don't have such magnets, such huge magnets having so much of magnetic strength to pull it out. So that's where we are going to be using it.
So that's all video and in a junkyard has made and they switched it on and then all the cross.
Yeah.
Like parts of the.
Any parts, any magnetic, any iron parts which are present in the junkyard that can very easily be separated by using an electromagnet. Is that okay?
Yes.
Right. Now, let's try to see what is a solenoid. Okay. Solenoid also basically uses a wire, right? And you are having any type of a cylindrical object. It can be a newspaper or it can be a stick or whatever it is. All that we are doing is taking the wire and winding it. Did you understand? And winding it, which will be more advantage. Suppose I have only 2 coils or I have 10 coils.
10.
Obviously, we have seen that increasing the number of coils can also increase the strength of the magnetic field. Now I've got one wire hanging from here. I've got another wire hanging from here. What do I do it? Join both the wires? No. Then combine both the wires.
Connect one.
See. Understand what I'm doing? Wire is here. I'm taking the wire. Okay. Winding it. Maybe I've taken 10 turns and I've got a wire here. What should I do with this?
Connect
Because it is an electromagnet. So क्या हुआ? So we have to connect it to the positive and the negative terminal of any cell and it becomes an electromagnet. What do I do? After that I'm going to just take it out. So what is left behind is a coil of many turns. Okay? Earlier days we had those landline telephone wires. You know what the coil of that thing is. So it is similar to that. You understand? So what is a solenoid? It is a magnet having coil of many turns connected obviously to a cell or a battery so that current can pass through. So the moment the current is passing through this coil, this entire thing itself is behaving like a bar magnet. Remember what a bar magnet has? It has a north pole, it has a south pole, it has got the magnetic field lines. Okay. So if you look at page number 201, look at page 201. Did you see the solenoid? How is it done? You have this wire and coil many times, okay, connected to the cell. Did you understand here? So this is your positive, this is your negative. Current is flowing in this direction and coming back here. So at every coil here, it develops a magnetic field because there are n number of coils, maybe 10, maybe 20, maybe 50. So the more the number of coils, obviously, more will be the strength of the magnetic field. But suppose we have no current, what happens to the magnetic field? Will it behave like a magnet? No. Okay, so a solenoid is nothing but a temporary magnet and it is an electromagnet. Have you all followed here? Why did we say that it is behaving like a bar magnet? Obviously because you have the magnetic lines of force Now this is where you have to notice it very carefully, that these magnetic lines of force, just as we are talking about a bar magnet from the north to the south, in this direction, from north to the south in this direction. Okay, so the same way here you have got these magnetic lines of force in this direction. Have you followed? And did you notice what is happening inside the solenoid? So if this is the north and this is the south, inside the solenoid it is from south to north. Did you all follow this? Is it clear? Okay? And therefore, I've just of course drawn only one of them. You will find that this is how it is going to be. Got it? Okay, come on. Let's read about the solenoid. Don't get distracted. Okay, can you read that? Magnetic field due to a current in a solenoid.
A coil of many circular turns of
Whatever, no problem.
दोनों एक साथ पढ़ेंगे
A coil of many circular turns of insulated copper wire wrapped closely in this shape of a cylinder is called a solenoid.
Underline. What is a solenoid? So the first line itself gives you the description of a solenoid.
Hard. The pattern of the magnetic field lines around this current carrying solenoid is shown in figure 12.1. Compare the pattern of the field with the magnetic field around a bar magnet. Figure 12.4. Do they look similar? Yes, they are similar. In fact, one end of the solenoid behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all the points inside the solenoid.
Where is it the same? Where are the magnetic field lines the same? Outside or inside?
Inside.
Did you see that inside it is parallel? Okay. So inside the solenoid, the magnetic field lines are the same.
That is, the field is in uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. When placed inside the coil, figure 12.11, the magnet so formed is called an electromagnet.
Okay, come on. All of you in your notebook.
Next.
Okay. What is a solenoid? Or define what is a solenoid, whatever the question is. A coil of many circular turns.
Have the same definition.
Yeah, finish. Coil of many circular turns of insulated copper wire. Why are we using copper wire? Yes, it's a good conductor. Insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Okay. And just below that, just write down a few characteristics of a solenoid. Okay, the next question. What are the characteristics of a solenoid? What did I ask now? What was my question?
What is a solid?
What is the
That's over.
characteristics of solid?
Characteristics. What are the characteristics of a solenoid? Anyone? What are the characteristics?
increases.
One of the solenoid is it behaves like magnetic and
It behaves like a bar magnet.
magnet when current flows.
Okay, very good. Then what is the second point? Is it a permanent magnet or a temporary magnet? It's a temporary magnet. Okay. How can you increase the strength of the solenoid? By increasing the current or by also increasing the coils. Come on, write down. First point. What are the characteristics? First point. A solenoid is a temporary magnet. Second point. It behaves like a bar magnet.
What are the first one?
Second point, it behaves like a bar magnet. Having what? North and the south pole. Okay, in bracket you can write it. Having a north and the south pole. Next point, the strength of the solenoid or the strength of the magnetic field in a solenoid. The strength of the magnetic field in a solenoid can be increased how?
By coiling.
Yes, by increasing the number of coils. Or by increasing the strength, the current in the coils. Yeah? Okay. Now everyone, very carefully, look at the diagram of the solenoid which is given in the textbook, or even if you have your volume, it is given there. You have the volume there? Don't bother about the time. I know when to stop at the bell.
I asked for the light.
Diagram? Anyone has the volume? You have the volume, you can use the volume. If you have the textbook, you can use the textbook. You have the textbook, right? Take off. Okay, come on. I want you to replicate the diagram which is given here. Next one. And I'm going to come around to see because it's a tricky diagram. Do it very carefully. Any kind of solenoid.
12 point.
No, 10. Along with the magnetic field lines. Now, Virat, don't replicate.
12.11.
See, I've drawn it here. Okay, same way. Quickly. Okay, how will you start? See here, start with the wire. Okay, show the coiling. Don't do so many coiling, just 3-4 you do because the diagram will be neat. Quickly. Once you have done the solenoid, complete the solenoid, after that using your pencil, you will draw the magnetic field lines. Do it, but do it right. Right now, you will do it right. Because this is a question which is going to be definitely asked. Anyone has volume 2? Do it correctly and label it correctly. See the direction of the current. And I want you to learn 4 points. Enough. Yeah. Show which is where is it going? Which is the dot? I was the sound. Look at the board, everyone. Look at the board. Now you have seen some of the lines like this. Where is it going?
Again, it's a bigger circle.
Yes. Have you all followed? I said, look at the board, everyone. Boys, you find a few of these arrows somewhere like that. What's happening to it? It just shows it's a complete circle like that. It's a bigger one. Okay, obviously they will not be showing everything. But the ones that you draw, just draw 2 of them, but draw it correctly. Why? If you don't draw, I will not allow you to leave the room. In your room. Never mind when you do it, I don't care. As long as it's correct. That's for your homework, boys and girls. Okay, diagram of the solenoid to be neatly done in your book on Wednesday. I'll check it after. Along with the totally wrong. See where it is coming out of the point. I will show you. It has to come inside the point.
Acid base and 9%.
Hey, how was acid base?
Easy.
जल्दी चलना खोलना
जाने पकड़ जाना भाई अभी लेडीज ये बड़ा भाई राजदीप को ज्यादा हमारे लिए कम
अभी जा रहा है।
अभी जा रहा है मैं
नहीं अभी